All right. Thanks, Cam. And would also like to specially thank Adam White, who insisted that I talk about doing science with robots. So Adam and I, we come from a tradition where AI researchers are seen as good old-fashioned scientists. So it's natural for us to see this emerging field of robot learning as a field of science. Although I already got a feedback from someone about the talk before it happened, which is that doing science with robot, that sounds vague. And I acknowledge that, and I'll try to clarify what we really mean by doing science with robots. So in this talk, we are going to clarify the following questions. First of all, why we care about doing RL with robots to begin with. And even more than that, why we care about taking more of a pure learning approach to robotics. Let's call that learning from scratch. So why does learning from scratch matter? And then we'll talk about why we should treat this emerging field of robot learning as a field of science, not just an application of RL. And finally, I'll talk about what do we really mean by doing science with robot and how we can do that. So these are the questions I'll touch. But before that, let me just say, this is the best time of all times to do RL with robots. We have all the interest and attention all around the world, backed up by the right kind of breakthroughs and demonstrations coming from board games, computer games, and simulated robots. So with simulated robots, we have general purpose deep RL methods that can be deployed to multiple different robot embodiments. And they can start from tabula rasa and even randomly generated behaviors. And without knowing anything about the particular embodiment a priori, they can still over time learn how to solve the given task. For the left one, the task is to reach the randomly spawned target shown by the red dot, and for the other two, the task is to go to the right as fast as possible. And the learning here is done by a model-free RL method called Trust Region Policy Optimization, TRPO. So after seeing all this, it seems like we are ready. We should be able to bring learning to robotics to at least solve these kind of tasks. So that's good that it seems like we're ready. There are all sorts of interest and reasons to believe that we can do that, but the question remains why we should do that, right? And by the way, this is a sort of kind of like a tutorial format, so I'd encourage you to ask questions anytime and allow me to ask questions to you. So you guys are here, so why you care about doing RL with robots? Anyone? Right, so there is an appeal to avoid hard-coded routines or control methods. Anyone else? Yes?
In order to understand the world, it may be necessary to be embodied into it.
To understand the world. And what is a better way than RL?
No, I'm saying like running on robots might be a good way to embody an agent into the world such that it can itself explore the world.
All right, yeah. So RL is a good approach, and to understand the real world, seems like we should use robots to do that. And yeah, anyone else? So these are all good answers. I was giving a talk on RL with robots at Vector Institute. I asked the same question. And a student said that we should do it because isn't that the whole point of RL? Isn't that why we should do RL? So many of us share this sentiment that robotics is RL's greatest battleground. But from the other side, also, in the robotics industry, there is a need for learning approaches. So there are many tasks, laborious tasks, where humans are involved. And superficially, they look dull. But if you look, for example, fulfilling packages in warehouses, but if we look closely, we'll see that people are using their intelligence and adaptivity all the time, right? So, and because the environment is so unstructured, the available robotic solutions, they cannot help them there much. So if we can bring learning approaches to robotics, the robotics industry will be able to relieve humans from numerous laborious tasks, which would be good for all of us. And here is the reason I care about doing RL with robots the most, which is this is a way to aim for the original goal of AI, which is to understand intelligence, including the biological ones, by designing and constructing new intelligence systems. And what is a better way than doing RL with robots for that? So this is the best time to do RL with robots, and we should do that, and we should even push further, which is we can now take a pure learning approach and try that with robots. And this is the least risky time to do that. And it's not also uncommon in RL to conquer a domain using a hybrid approach, only later to come back and reconquer it using more of a pure learning approach or learning from scratch. And in robotics, hybrid approaches, they are popular, quite popular right now. Here, the control methods are heavily engineered based on analytical methods, where some of the parameters are exposed to learning, or suggestions from learning methods, they are incorporated with the control method to fine-tune it. And among the approaches that lean more heavily toward learning, there are two of them that are predominant. One is imitation learning. So in imitation learning, the reliance on humans is mainly confined to generating demonstrations, either manually or by writing a script. And then the learning methods, they try to mimic that demonstration. And the second one is simulation to reality transfer. Here, learning often happens completely from scratch, and reliance on humans is shifted to developing a high fidelity and representative simulator. And this is one of the best examples of that, coming from OpenAI. And this is a great way to attempt learning from scratch, but we can do even better than that, which is learning from scratch in real time. Not in simulation, but using real hardware, and starting from tabula rasa and from random behavior and exploration, how to learn to solve a task. And this is not quite popular or common yet because it's hard. And we only have some examples coming every now and then. Here we are looking at two examples. On the left, it's learning to dock to a charging station, and on the right, it's learning to walk by its creature, robotic creature. And these are modestly complex, and but I also should say that these are not any simpler than the usual benchmark tasks that we use in simulations. So this is what this talk is mainly about, learning from scratch in real time. How can we do that? And probably before that, why we should do that? I care about it deeply, but how are you guys? Again, anyone? Why this matters? Yeah. Simulations are?
Well, building simulations that are complex is really hard. Like, you want to have agents that do very complex things in
Right, so sim to real is fine, except that it's not really solving our problem. Okay, that's a very good one. So we eventually have to face the reality and do the learning, because our robots will be deployed in unstructured environments, right? And they have to face new challenges. And who is going to build in real time a new simulator and solve it using 100 years of simulation experience? It's a very good one. Anyone else? Yeah.
Maybe we don't know all of the challenges in the real world and we cannot simulate all of them.
Right. So
You have to like deploy and see what happens, what kind of problems.
right. If we could simulate everything that a robot is going to face in the real world, then sim to real should be fine. But then it seems like probably we'll have to solve a bigger problem, which is to model the whole world first. So these are very good answers. Here's another answer, which is in applications for example, in the industry, we sometimes and often we care about like a superior performance fast, and learning might seem like it would take a long time. But once we solve the hardest of the problems, which is to learn from scratch in real time, the reasons to believe that it might be easier to then later come back with expert knowledge and combine it with learning approaches more flexibly. So that's one reason. Another reason is we are trying to understand mind computationally and scientifically in AI. And when you are trying to understand things computationally, a good rule of thumb is to go for a description of the explanation that has minimal length or short length. And what is a better way than removing expert knowledge and going for a pure learning approach and explaining the whole agent system using a learning algorithm for minimizing the description length? So learning from scratch that way deepens our scientific and technological understanding of mind. So that's why I care about learning from scratch in real time. So now, if you all are on the same page with me, still the question remains, that is, what science has anything to do with that? Yeah.
I have a question,
Yeah.
quick question. So deep learning kind of changed the whole computer vision field.
Yeah.
Because CNN, they work really well. But my concern / comment is that we still haven't seen many end-to-end learning approaches that's really applicable on real-world problems. So why would we want to throw out all these knowledge that's been developed over these years in robotics, controls, robotics, dynamics, simulations, and just stick to end-to-end learning and learning from scratch?
So the computer vision applications, they are real world applications. So you mean like real world robotic applications, right? So my guess is the same is going to happen for robotics. Now we don't have good solutions, so we have to rely on hand engineered right solutions, heavily engineered solutions. But we will come back and have end-to-end learning in robotics. That's the goal, right? So right now we are not proposing to remove all the solutions we have. But as some of us already mentioned, why we need end-to-end learning, there is a need for it in the industry. There are unstructured environment. And as the existing solutions cannot address them, we actually want to do R from scratch. So if we have them, it is desirable to use them instead, or maybe combine them with the engineering-based solutions. That would probably be the best of the worlds. How about that? Would you be okay with that? If we have a superior solution that the industry needs, would you be okay to combining them with engineered solutions or making them obsolete? Yeah, you think so? No, because kinda. So yeah, what's your reservation against that?
I don't know, maybe it's more of an offline talk, but
Yeah.
I kind of feel like end-to-end learning is hard to debug, it's hard to interpret the system, and it's not applicable for something that really happens in the world, like autonomous driving. That's my intuition.
Right. So even for autonomous driving, if you can as Ian Peters already mentioned, that if you can build a model and learn good policies there, and at the same time you can debug them well, would you then accept that?
Yeah.
So those are separate problems. Those are hard problems, right? But even before that, we don't have end-to-end learning for robots, right? So if we have that, then we can talk about how can we make them explainable, how can we debug them, and if they work well, and the only problem is that we cannot debug them, I'm sure people would be interested, like people will use their resource to understand how to do that well. But right now, we don't even have that, and we are trying to address the question like why we don't have that, and what we need to do. Okay. So what we need to do is do science. That's the answer, but it's not quite an agreed upon point of view. And there are actually many common views against treating robot learning as science. So here is one. So robot learning will benefit most from demonstrations like AlphaGo than anything else, including science. So how many of you agree with that? Some, few, all right. So it is true that working on demonstrations like AlphaGo is not the same thing as working on the scientific aspect of robot learning. It's a different thing. And given finite amount of resource and time, we'd have to choose what we are going to do. And if this has the most impact and more maybe glory, then maybe we should go for that. But here is a thing about AlphaGo, which is that it didn't happen overnight. It happened because there was a supporting scientific community which worked on the field of learning and search for decades. And that's how it happened. And in order to make that happen for robot learning, we need that support. Do we have a scientific community working on robot learning dedicatedly? Right? So this is more of a reason we should do science in robot learning. So here is another opposing view, which is, again, robot learning will benefit most through industrial applications. How many of you agree with that? Again, a few. Yeah, you have a question? You agree? And again, this is a different thing than doing science. But coming from industry, I can tell you that people in the industry, they are not any less rigorous. And for solutions, they look at papers and reliable, stable technologies, as well as advanced technologies. And when they're looking for solutions coming from robot learning, what they find is that like learning in simulations, right? And when they try to apply that on robots, they don't work. And when they find a real-world robot learning, oftentimes it's nearly impossible to reproduce those results because they often appear as the last demonstration in a paper. Instead, if we had a dedicated field that explains how to do robot learning properly, the robotic industry will benefit the most, I would say. So this is another reason we should do science in robot learning. Any question? Yeah.
Do you think advancing the science in robotics wouldn't benefit the industry in the long run?
Wouldn't benefit or would benefit?
Wouldn't. Or wouldn't.
No, so the argument is it would. We have to do science, especially in the field of robot learning, so that when in the industry someone tries to solve a real problem and create an application, they have a solid backup from the science.
It's like just structuring the problem in a way that is easier to solve in a wider angle, so it should be beneficial for the industry as well, I guess.
Yeah, that's right. So that's precisely why I'm bringing this opposing viewpoint. This is actually an argument in favor of doing science in many ways. So here is my favorite opposing view, which is that is just hard. And I like it because it's honest, it's true, right? And it's okay, like if we don't do science because it's hard, it's okay. Because we will end up doing science for robot learning only if we care about it. And when you care about something, then the hardness of the problem tends to matter less. So here is a not so common view. And it's my view, which is that we, at least some of us, should do science in robot learning all the time, for all the above reasons. How many of we agree with that? Okay, cool. It's the majority opinion so far. You have a question? All right. So this is why we need science, rigorous scientific experiments in robot learning. Now, but what does doing science even can mean? So among many different things, science brings transferable and reusable knowledge. And how does it do that? To understand that, we don't have to go any further. In the machine learning community, we have a checklist to encourage reproducible research, right? And how does it help? For example, when we make claims in our works, it's often possible to make inaccurate claims mistakenly. So what this kind of reproducibility checklist does is that it shows us what are the common pitfalls and protects us against that so that we can make more accurate claims. But of course, there are others among us who always make accurate claims with fantastic works. And this kind of checklists, they also help these researchers by helping them to make more precise and more accurate, more shareable claims and results, so that others can benefit from these research. So I looked at the checklist carefully, and it's overall the goal seems like for reproducible research, it seems like the goal is to reduce uncertainties around what we claim and we know. And a checklist alone is not enough for that. And it's just the tip of the iceberg. We need a whole community that will help encouraging giving more details, establishing benchmarks, and establishing guidelines for analysis and experiments. So here is a good example. So here we are looking at learning curves from two different experiments. So this kind of learning curves we show usually to claim that one algorithm performs better than the other. And these experiments were done on a popular benchmark task called in simulation called half cheetah. And here it seems like one algorithm beats the other, but both learning curves were run using TRPO and the same hyperparameter configuration. So then it seems like the TRPO beats TRPO, which is a nonsensical claim. But this can happen if we run, say, 10 experiments and then pick the best 5 to draw our learning curve. So what is the problem with that? If we run 10 independent experiments and draw our learning curve with the best 5, what could be bad? Yeah. Yeah. So it is not independent anymore, right? So reproducibility checklist and the practice in the community around it helps us to avoid this kind of pitfalls. So in machine learning community, we established proper ways of doing scientific experiments in order to characterize or reduce the uncertainties involved in experiments. But we don't have that for real robot experiments. And here is an example. Here again, we are looking at learning curves from different learning experiments. And they are all done using real hardware in real time, starting from tabula rasa. And it again looks like one algorithm beats the other, but all of them were learned using TRPO, the same algorithm with the same hyperparameter configuration, and they also share the same randomization seed. So if we ran those experiments in simulations, then we'll have overlapping exactly the same curve. But in real world, it turns out that they are different. Why? Because among these experiments, the software setup was slightly different between each other. And those are often not explained in our experiments, let alone knowing that how to set them up correctly. So this means that one research group may claim that learning works quite well with TRPO, and the other may claim that we get the red curve, it doesn't work at all, there is no learning. So it means that there is a lot of uncertainties involved, more uncertainties involved in real world robot learning compared to what we have in simulations. And we haven't discovered those unknowns yet. So doing science would mean primarily, and to begin with, understanding and characterizing those uncertainties. And if we can, to reduce them. So let me give you examples of how uncertainties can be included in an experiment. For example, through stochasticity, like the random initialization of the network, that's an uncertainty that is inherent, and we cannot reduce it, but we can characterize it. And there is uncertainties that we often include to complexify the environment or make it more realistic, such as the sticky action that is included in the new release of arcade learning environment. And there are other uncertainties such as like not exactly knowing how the experiment was done. That's due to the lack of details. And those are what we can reduce. So for the rest of the talk, we will try to do these two following things, which is we'll try to establish a benchmark task for a real-world robot learning task. And second, along the way, we'll try to discover the uncertainties involved in real-world robot learning experiments. All right? Any question? Yeah.
If we want proper benchmark, we would need like the hardware to be the same for everyone, right? And like in terms of hardware, it's like unrealistic to have every lab that has the same hardware.
Right.
And for like physical robotics system, if we don't have the same hardware, we cannot do proper benchmark.
Right, that's a limitation, but that's not really a big problem, I would say. Because in the end, the science and the application of robot learning will be done by people who really are motivated to do that. Like in the industry, you will have to buy a license for Mujoko, right? So, and if you care about it, you'll end up buying it. And it's not the same as like buying a robot because you have to set it up. But if you're working on an application, you have to set it up and you have to know how to do that anyway, right? And so that's why there should be a community working on it dedicatedly so that there will be varieties of robots for which we know the specifications of how to set up the task. So it's a good thing, right? It would be part of it. It would be an essential part of it to have similar robots. And if we are trying something new, but a lot of it would still be transferable. A lot of the knowledge that we discover would still be transferable. Yeah.
Do you also recommend like having a benchmark robot, as what he said, but like a very minimum viable sort of robot that just works for everyone with like least cost, I don't know, $200 or whatever?
Oh yeah, that would be great. And people are working on that, right? Yeah, that would be really great because right now the example that we are creating here, a benchmark task, that would use a robotic arm, a costly one. But later I will also talk about other options that are much cheaper. All right, so let's try to do that. But before that, the fundamentals. We will talk about reinforcement learning control tasks, and mainly episodic tasks. And I hope we know about this diagram. It's an agent-environment interaction diagram. Here, an agent interacts with the environment by taking an action, and in return, the environment changes its internal state, and state is here in a Markovian sense. And the environment also provides the agent the reward. And reward is how in RL we specify the goal. A slight modification to the original diagram, which is that the agent doesn't get to see the state of the environment. Instead, it sees a partial snapshot, an observation. So, given this diagram, then there are three main components of an RL task, which are the observation space, the action space, and the reward function. So these are the things we have to specify mainly to define a task. And this is what the life of an agent looks like in simulation. So here I would like you to look at it carefully. This is a well-standardized way of interacting with the environment by an agent in simulation. So this is a loop. In the first step, we're computing the action based on observation. Usually it is done using a map. And after that, so the action is usually represented by a probability distribution, where the parameters are often modeled by, say, a neural network. So when we compute the action, then we provide it to the simulator to compute the value of the control variable. It could be the joint torques of a robot creature in simulation. And then after that, we advance the simulator using physics equations by a constant amount of time. And after that, we extract the sensory motor information from the simulation, construct the next observation vector and the reward. And then when you have all this information in this one cycle, then we can make a learning update. And we would usually make a learning update if we are doing incremental model-free RL. For example, the Q learning update will fit well here. So this is usually what we would do in simulations. And this is one action cycle, basically. And here is an example of a benchmark task in simulation. This is Mujoko Richer from OpenAI Gym. So here the task is to reach those randomly spawned targets by the tip of the arm. And here the robotic arm, it has two joints that are controlled on a moment-by-moment basis using, say, deep RL here that learn this policy. And to define this task, we need to specify three things: observation space, action space, and the reward. Okay, so here is the question for you. What would be the reward function here? Huh? But more specifically, 1, 0. When you are at the goal, 1, other 0. Okay, all right. Anything else? Yeah? Distance to the goal, that's a good one to make it dense. Yeah?
Is this the continuous? So like the time it spent at the...
Discrete time.
Oh.
Yeah.
So we can like give it reward for every second it spent at the goal.
Okay, yeah. At the goal. That would be quite sparse though, right? Because you'd not end up at the goal randomly quite often. That's also a good one. So this is the specification of the task for Mujoko Richer. So observation space, it contains information about the joint angles, joint velocities, also the target position in Cartesian, and the vector difference between the target and the tip position. And the action space is the joint torques. So that's the task, and we would like to make a task similar to this using a real robot. So the robot is UR5. It's a robotic arm which has 6 joints. And it has mainly 3 devices, the arm itself. And one specific thing about it, about the robotic arms, the tip of it is often called tool center, because that's where the tool or the hand or gripper will be attached. And then there is a control box that is a computer that runs the internal controller. It's known as UR control, and it can be programmed using real-time scripting. And there is also a user interface using which we can configure or even control the robot with the touch screen. So that's our robot, and that's how the communication with the robot works. So the UR control communicates with the robotic arm using a C API and using a cycle time of 8 milliseconds. And we communicate with the robot through UR5 using an external computer. So there are 2 modes of communications, read and write. So we can establish a communication to get streaming packets from your control by using a command like socket receive, and then we'll get packets 1 every 8 milliseconds. And we can also send the robot command once every 8 milliseconds by using socket send command. So this is important because there will be an exercise later based on this information. So if you want to look at it closely. Now, so how do we control UR5? What are the actuation commands? So in Mujoko Richer, we said that the action space is the joint torque, right? So that's the usual way of controlling robots in simulation. We provide the instantaneous torque, and then it's easy to incorporate into the physics simulation. But how we are going to do that for UR5? So there are different control modes, and they vary along 3 main dimensions. One is it's either a long-term persistent control or a moment-by-moment control. Second is we either specify the position or the speed of the joints individually, or we specify the position of the tool. And third is we specify either the position or the velocity that we desire to achieve. And those are the 3 different dimensions, and now we have the job of specifying a benchmark task. But these are like more trouble. These are more uncertain because we have to choose one, pick one, and which one we should pick to create a good benchmark task for RL. So for each dimension, we have to make a choice. So let's go through each of them one by one. So which one would you choose for the first dimension? A long-term control or a moment-by-moment control? Which one fits more with an RL task?
I think moment by moment fits better with RL realm, but persistent fits better for physical systems.
Okay, all right. Yeah, usually when we use control methods, we would use probably persistent control. But oftentimes, even with motion planning, it's more flexible to use moment-by-moment control. And as you said, for RL, it's a better fit. And also, the pulse space that we can obtain by moment-by-moment control contains technically all the pulses that you can obtain with the persistent control, right? All right. So moment-by-moment control goes better. And then between joint space and tool space, which one would you choose? Any question? If you need clarification for those 2 controls? Yeah?
I think joint space, because if we do it in tool space, then there needs to be another component and another controller to translate it from tool space to joint space.
There you go.
There's like more components.
Right. Although your control allows you to specify the tool space position or velocity. But what it would do is then it would use inverse kinematics. Right? In the end, it would send commands to the arm on a joint by joint basis. So it seems like it would be more direct to use the joint space. Right? And there's also position versus speed. So let's do it later. Let's see how a random behavior would look like in this benchmark task. So this arm is now being driven by random motions. Right? So here we are doing moment by moment control in joint space, and the commands are speed commands. And let's compare that with Mujoko Reacher. Right? We're not quite there, right? It would be great if you can explore that much so fast. But we couldn't, because we are producing these random motions, and at the same time, if we have a high speed, what happens is that it moves so violently that it shuts down the whole system. Right? There are protections against those kind of behavior. So we had to reduce the speed, and that's what we get. We'll come back to that. Now, what do we have? So superficially, it looks like we are almost done, which is that we are gonna mimic Mujoko Reacher using UR5. So we are gonna control only 2 joints, and there will be randomly generated targets, but they will be well defined. So our observation space, they will again contain the joint angles, velocities, and also the vector difference between the target position and the tip or the tool space, the tool center. And the reward function would be similar to what we had, which is a negative distance, Euclidean distance between the target position and the fingertip. And the Mujoko Reacher reward function also had a penalty for taking large actions. And we drop it here for simplification. So that's what we have. Are we done? Are we done creating a benchmark task? And did we take care of all the uncertainties? What is left? In simulation, we will already be done. Yeah?
I was just going to say that you're still engineering the reward, right? Like you can always do this.
You're right. So as I mentioned that there are 3 things we have to specify to define a task. So the reward function is part of that. And although we didn't engineer it more than what is done with Mujoko Reacher. In fact, we simplified it, right? So, but you're concerned with reward engineering. You don't like that. Right. We can come back to that. But Mujoko Reacher is a well-established and widely popular benchmark task. We're trying to see whether we can do that even with real robot. Yeah, you had an answer to what is left.
The action is still missing. Like, what would be the output of the policy?
What would be the output of the policy? So, as we saw before, that we were almost done. What was missing? What did we not choose?
Position versus.
All right. But if we choose that, that's done. Yeah. Okay, anything else? Yeah? Sorry? Yeah, it does matter. So that's something we didn't specify. And that's kind of like part of all the things that we have to specify and we have to be clear about. And we show that that actually matters. Anything else? So, as you mentioned, one is the mode of connection, whether we are going to make a so the connection, the communication we can make from the external computer to the UR control, it's over TCP/IP. So it can be wired or wireless. And the question is, which one is to choose? Which one would be better? And again, we didn't decide on position versus velocity and cycle time of the action. That's not decided how fast we should take the action. And also we showed that how the life of an agent looks like in simulation, like the pseudocode. Can we use that directly? Is that the most efficient thing to do for real robots? Or we could do something else? So those are still not decided. So let's go through them. We want to see which one is better, wired versus wireless. But do we have like already a prediction which one we should go for, wired versus wireless? Anyone? Yeah? Wired? Because? Right. That, and it is connected to the overall goal, which is to reduce uncertainty. And wireless communication would have more uncertainty involved. But we try to confirm that, like how much uncertainty we have with wireless connection. Would it bother us, right? So to see that, we received packets back to back from your control, 10,000 of them, and then measured the median and the 95th percentile among other things. And let's make a prediction. So this is a fun exercise, which is every time we draw a plot or run experiments, before that we can make a prediction. What is to expect? And it's a good way of doing science. Right? Before running the experiment, form a hypothesis. So what would be the median for wired and wireless connection? So what is this cycle time of communication? You remember, anyone? That slide that I asked you to look closely? 8 milliseconds, huh? Right. So what would be the median for wired communication and wireless communication? Let's make a guess. And what would be the 95th? So here is an answer, which is wired would be kind of like 8.2, 95th percentile 8.5, wireless 9, and 12. How many of you think that that's the answer? No? No one? How many of you think that's not the answer? Okay, rest, we are not sure. So here is another answer. How about this one? Yes? Median 8 for both. Yeah? Does that make sense? Wireless will have the same median?
It depends on what kind of network you have. If it's a very private network, like you have your own router and you are just connecting one device to that router, then it may not be very high.
Right. That's what we had. It depends on the wireless connection, exactly. Right. So that's the answer. The median was the same. There was a lot more variation in the packet inter-arrival time. So our hypothesis is confirmed, which is that we shouldn't use wireless. There is a lot more uncertainties involved, and we're trying to reduce uncertainties. So that was easy. Now, what's next? Position versus velocity. Before we do that, any prediction? Which one would be good to use? Should we specify target position on a moment-by-moment basis, or should we specify target velocity for real robots? If you want to use real robot, this is something you have to decide. And based on what you choose, the performance can be different. Right? It's not clear, right? Yeah.
Maybe angular velocity.
Maybe angular velocity, right? So we already chose joint space control. So whichever it is, it will be angular.
Yeah, so we have the mapping of the length of the arm.
Yes.
So if we have a mapping of angular velocities, then we can map the velocity of the different ends of the arm.
Right. That's right. So that's the constant amount. It can be learned. So, and we already chose the joint space control is better. So it has to be about angles. The question is whether angular position or angular velocity. So you're saying angular velocity. All right. So let's see. So what we did is we moved the robot randomly again with randomly generated commands. Right. So in one case, we want to do it for position control. In another case, velocity control. Now, when we generated random velocity commands, it moved, we saw it, how it moves, right? We tried the same with position control, and it didn't work. What happened is the whole system was shut down, right? Because randomly we were specifying at one moment to go at this position and at the next moment completely in a different position. And the robot is trying to do that, and it creates an abrupt movement and a violent noise. Right away, boom, shut down. So we couldn't do that.
Maybe because in case of angular velocity, we need an integrator, not an integrator.
That's right. Then we tried displacement, angular displacement, and integrated it once. Again, it was less violent, but still shut down the system. Then we went for second order displacement, and that kind of created a smooth motion. So in one case, our action was integrated twice to get the target position. In the other case, we used the velocity command, right? And then we looked at the incoming packets, and we measured the correlation between the actions and the future robot state variables. Some of them. It's also known as cross-correlation, right? So this is the result we got, and it was quite surprising. So let's look at the blue bar here, which is the correlation between the velocity as an action, and for the left plot, we are measuring the correlation with the target acceleration. With different lags in future, the target acceleration goes in future. And we don't have any significant correlation in the next cycle time. Whatever action we choose, in the next 8 milliseconds, the robot does not respond to that. The arm does not physically respond to that, right? And it only starts to respond from the second cycle time. But that's only an internal state, which is the target acceleration. That's a variable within your control, and this is what it is it thinks that it would apply in the next cycle time to the robot. So to have any physical measure, we had to wait until the here, this blue bar, wait until a lag of 3 packets, 3 cycle times. Only then we had any significant correlation. So that was interesting. Another interesting thing is that the relationship between action and subsequent observations, that was quite tight for velocity control, but not as much for displacement control. So here we can see that we have a correlation here, but nothing significant after that. The same is almost true for this one, but for the displacement control, we have still some correlation, some lingering effect, right? So this makes us go for velocity control. It has a cleaner relationship between action and subsequent observations. So we updated our specification of task. We added target joint velocities, but we also noted that there is like no clear cycle time that we can choose for action. What should be the time step? It's not clear, right? So the observation space is not going to be as clean as we have for simulation. That's why we also included the previous action in an attempt to make it more Markovian, although it doesn't guarantee it. All right, so what's left? What should be the cycle time, the length of the time step? Any answer? Is it clear that what it should be? It's not, right? So one answer is just use the pseudocode that we had for simulated task and have 8 millisecond cycle time. That's one to use naturally because that was the only cycle time we have seen so far with UR5, right? But we also saw that nothing happens in 8 milliseconds. And is it a good idea to use this sequence of computations? So these are the task and agent related computations we have to do, even in the real world. But is this the right sequence? So two questions remain. What should be the cycle time and in what sequence we should do? So here is an exercise for you guys. If you have been attentive, you'd be able to do that, which is let's create a new way of communicating and doing the task and agent related computations for UR5 by redistributing these computations in an efficient manner. So this should involve a read call in an 8 millisecond cycle time and a write call with the same cycle time. And also we should look for ways to make the communication more efficient. For example, you see that we made a learning update right after we constructed the observation vector, but this might not be the best thing to do with real world applications. Why? Because right after we constructed the observation vector, now when we are making a learning update, the real world is moving, the arm is moving away. Whereas in simulation, when we make any of these computations, the simulated world, it stands still, it does not move. It only advances at step 3. It's not true for the real world. So it's not clear that this is what we should do right after observation vector. So if you have a better idea, let's do that. You can use multiple parallelly running processes. But let's do that. Let's take 5 minutes. Use your pencils and papers or computers and see what you want to do. These are the steps we have to do, but for real world. Any question? Masood? Hey. Is the question clear? Huh? Okay, there you go. Thanks. Yes. So, in order to communicate between the robot and the agent, or the world and the agent, these are the computations that we have to do in simulations. If you look through them carefully, right? We have to compute the action, which is often does using a forward policy pass, and then we send it to the world, and then it's advanced by time, and then we extract sensory motor information, and then we construct observation vector and the reward, and then we make a learning update. These are necessary things to do, but this is how we do in simulations. So we have to do all these steps for the real world, or in what sequence you would do. And answer is that let's just do exactly this way. Right? That would be a good answer, maybe. But is that the most efficient way of doing things?
Like we would have to increase the number of observations. No, the set of observations, because we have so many parameters along with those observations. So the tuple of our one observation would be more than what we would do in a simulation.
Okay, so then the concern is it would take more computation to construct the observation vector, because it's probably much bigger potentially.
Yeah.
Is that the concern?
Yeah.
Okay, and yeah, so another concern is there might be more than one robotic physical device in your robotic system. There might be one arm, one camera, some other servo motors for the gripper.
Sensors.
Right, other sensors. And they all are sending, actuators. They're all sending packets, right? And then they may have their inherent cycle times that are different. So running at this cycle time, how would that gonna work? Yeah?
I'm not sure if that's the right answer, but the way we usually do it is like we have one time, like global timestamp in ROS, and then everything is synced, and then we just use that, and then we subsample on that.
You
So,
subsample.
for example, the robot might run in like 50 hertz, but we subsample it at 10 hertz, and then we use those samples in order to reduce the noise and also the effects of any other.
So UR5 is 125 hertz, right? 8 millisecond.
Sorry?
UR5 has a cycle time of 8 millisecond. Let's say I have another device, a camera. It probably has 50 hertz. Or a servo motor. It has a different, like cycle time is 2 millisecond. How do you just set one global timestamp? Right, because you have to collect data from all those devices at their own cycle times that are specified. Yes? Buffers. Well, if buffer is the way to go, is more efficient, we should do that. That's a good answer. Yeah? There's nothing against it.
What do you mean specifically when you say efficient? You ask us to think of this in a more efficient.
All right. So here is one way of thinking about it. So one is to reduce uncertainties. If things are more stochastic, then it would require us to, for example, do more runs. That would be inefficient. So efficiency would be reduce that uncertainty so that we end up doing only less number of runs. That's one way of doing things efficiently. Another way is not sitting on an information or an observation for too long. That would be inefficient. It doesn't matter for simulation. You get the observation from the real world, from simulator, and then you take as much as needed through your CNN, but the world doesn't move, right? So it doesn't matter. But in the real world, if your network is quite big, your army is going to move away. So it's better to compute the action as fast as possible. So now the question is like, what should I do? After I get the observation, should I make a learning update? Should I do a forward policy pass? Both are not equally efficient in that sense. Yeah? All right, so this is what we did in one of our works. So there are multiple processes and threads, and all the steps that we saw for simulated tasks, they are redistributed here among those processes. So there is one dedicated process per physical device. It's kind of like a driver. It will have two I/O threads. One is to get the packets for UR5 at 8 milliseconds using a blocking call, and there is another one to send the commands. And as soon as they do that, as one of you mentioned, they are stored in a buffer, right? So, and on the other side, we have another process for doing agent and environment-related computations, and they are also done using two parallel threads. The environment thread, all it does is that it constructs the observation vectors looking at the buffer as soon as something arrives from the sensor thread, and also the reward function. And whenever an action is computed by the agent thread, it right away updates the actuation command and sends to the actuation thread. So the cycle time of this is really short. And then we have an agent thread. When it wakes up at a particular moment, it looks at the most recently available observation vector, it computes the action, and then it makes a learning update. And after that, it waits until the cycle time is complete. So if you notice here that we did something different here. The order of computation is flipped. In simulation, right after the observation vector is created, we make a learning update. Here we do the opposite. We compute the action first, and then we make a learning update if we are ready to do that. Okay, so how many of you got this right? There was a great work actually done showing how actually this matters here at UFA, at Patrick Pilarski's lab. So now let's see what are the remaining uncertainties. So we created this asynchronous architecture, so that would be our baseline setup. And then we created variations to it. In one case, we added random delays to have variable cycle times. in one of the threads to the agent thread. And in the other case, we added random delays to the actuator thread, right? So this one, here we added a random delay to this thread. So that would create a variable cycle time. And in the third case, we added random delays to the actuator thread. That would again create a variable cycle time for communicating directly with UR control. And then also we used wireless communication. So those are the 4 different setups. And let's make, again, predictions. Which one worked best? So number 1 worked best. How many? Yeah? Yeah? Okay, how many of you would think that number 1 worked worst? Not the best. How about not the best? Yeah? Yeah, okay. All right. And which one was the worst? Any guess? Wireless was the worst? Okay. It could be. Actually, it depends on the setup, right? And among these two, when random delays are added to the action cycle time as opposed to the actuation, which one was the worst? Given, say, the same amount of delays. Same, because what does it matter is the same amount of delays in the whole system, or does it matter actually? Right? One is where we added variations here, random delays, one is over there. Which one would be worse? So this was actually surprising. The worst was when we added delays to the actuator thread. There's a thread that's closer to the device. Delays added closer to the device would harm more. And of course, wireless was also worse. And the best was our baseline setup, where we don't have variable cycle times. We try to control the system as much as possible. And this is how the behavior looks like after learning, right? So Reacher, and compare it to Mujoko Reacher. It's not quite there yet, but it's only a few hours of experience time. Now, we tried to discover the involved uncertainties in a real-world experiment, right? And we tried to characterize them, reduce them, and now we are trying to see whether our experiments can be repeatable. So what we did is that we ran the same experiment with the same randomization seed multiple times. And we found that they look quite repeatable, overlapping, ups and downs are similar, and yeah, they're close together. And we again ran the same experiment 4 times using a different randomization seed. They also look similar. Right? So if we ran those 2 different sets of experiments in simulations, what would we see? We would see exactly 2 learning curves, because in computers we'd make everything deterministic because the randomization seeds are the same. And there will be 1 blue curve and there will be 1 orange curve. That's it. So it's not quite expected to see that in real world robotic experiments, but that's what we got. And in a subsequent work, it actually tightened up a bit further, right? So we worked on it a little bit more. We described like how we reduce further uncertainties. And then over here for the blue curve, if you look closely, there are 4 experiments, there are 4 learning curves. They're so tightly overlapping that it's hard to see. It's quite repeatable. These experiments now are quite repeatable. And now that we are confident with our real robot experimental setup, now what we did is that we created a benchmark task suite. 6 different tasks, real robot tasks using 3 different physical robots. UR5, a servo motor by Dynamic Cell, and This is known as Roomba. This is a research version robot create. And there are 6 tasks that we developed. And we released all the setup and the code through a project called SenseAct. And it's to encourage a reproducible research. And then we were able to run experiments that we usually do in simulations, which is to do hyperparameter search. The 30 different hyperparameters configurations we tried for 4 different algorithms, TRPO, PPO, SoftQ, and DDPG, on 2 different robots. So the goal here was to choose the best hyperparameters from these algorithms and then see how they work on the held out other 4 tasks, right? And each of those blue dots, they are one independent experiment. And overall here, we have about 500 independent experiments and about 1,000 hours of robot experience. And these are the results for 6 different tasks. In most cases, the best hyperparameters that we chose, they were able to learn an effective policy. They were able to solve the tasks. Although, we also compared with a scripted agent. For example, for richer task, it was based on decades of scientific and technological advancement, a PID controller, and we couldn't beat that. So one reason was, if you remember, that we had to reduce the speed in order to allow random exploration. So that was a limitation. Although you have to note that this was based on decades of scientific advancement, whereas here the robot learned starting from tabula rasa and was only trained for a few hours. But in a case which is to dock to a charging station where we don't have clear answers how to do that, how to script that, the learned agent was actually doing comparably with the scripted agent. So that kind of shows what kind of robotic applications we can expect, where we can see robot learning more. It's probably where we don't have clear answers from classical robotic methods. And this helped other labs to do reproducibility and original research. For example, to the left, we have a result from University of Toronto Aerospace Institute. Oliver Limoy, he tried to verify our claim that if we run the same experiment with the same randomization seed twice, can we get nearly the same learning curve? And he corroborated our claim there. And this one is from a PhD student from Denmark, and he also verified whether they can use SenseAct to solve the research problem effectively. And to answer one of your questions about cheap robots. So those are also coming. This is from UC Berkeley. They created this robotic arm with the task of grasping. And it's quite cheap. It's a few $1,000s. And they provided all the specification of how to set up the robot, including all the code. So these are happening this year, and more to expect. So time to conclude. So what do we expect next? What did we achieve? We are trying to understand and characterize the uncertainties involved in real-world experiments. And by doing that, we would be able to make RL algorithms that are more ready for applications, more ready for robotics. And here are some examples. For example, real-time learning experiments, they come with some strict requirements on the computations and the timing budget, right? So, which means that some algorithm will do better than the others. So if we know the requirements well, and as AI researchers, we are trying to design algorithms, we would know better what algorithm to design and how to design them. So this will shape our development of algorithms. And second, when you looked at the random behavior, it was not as good as Mujoko Reacher, right? And it was basically actions drawn from normal distribution, and they do not work well. They are quite inefficient with real robots. So we need to look for better exploration methods with physical devices. And here is another one, which is in the production setup. There are different hyperparameter configurations that are more desirable. In simulations, what we do is we create an algorithm. It comes with many hyperparameters, and we try to tune them, find the best one, and we show that the choice is quite robust across different tasks. But those choices, they have real implications in the real world. For example, how many times you're gonna make an update per time step, or how big would be the batch size. They have real implications. So based on that, in the production setup, or in real applications, there are some hyperparameter configurations that are more desirable than the others. If we know those, if we know what hyperparameters are more compatible with real-world experiments, we would, from the beginning, design our algorithms to satisfy those conditions. And again, this is the best time to work on robot learning and to so this robotics application is not going to happen magically, right? We have to create this supporting community, and we have to lead our way for the coming generations of robotic scientists. Thank you.